Let's recap time dilation. For time dilation, under special relativity, time passes slower for an observer who is moving relative to another observer. If delta t naught is our proper time interval, and delta t is the time interval measured by an observer not in the inertial frame of reference, then the time interval delta t is equal to gamma times the proper time times delta t naught. We're going to apply this time dilation to an example problem. The period of a pendulum is measured to be 3 seconds in the inertial frame of the pendulum. What is the period of the pendulum as measured by an observer moving at a speed of 95% the speed of light with respect to the pendulum?
In this problem, we are going to apply the concept of time dilation. The period of a pendulum is measured to be 3 seconds in the inertial frame of the pendulum. So the inertial frame is the frame of the pendulum that's moving with the pendulum. What is the period as measured by an observer moving at a speed of 0.95 c, or 95% the speed of light, with respect to the pendulum? All right, so when I think about these problems, I draw two little rooms. Okay, my first room up here is my inertial frame. Okay, this is my inertial frame. This frame of reference is moving with my pendulum. So in this room, my pendulum is hanging and it's swinging back and forth like this, right? And we said that the period of the pendulum in this frame is 3 seconds. So there's going to be somebody here in this same room where this pendulum is hanging and swinging, and they are going to be taking that measurement. This inertial frame, we're going to say, has no speed. Okay, and so what is the period of this swinging motion here as seen by an observer moving at a speed of 95% the speed of light with respect to the pendulum? So down here in my second room, I've got somebody else who's in here, and they're watching this pendulum swing back and forth, but this is moving at a speed of 95% the speed of light. Because they're moving so fast, so close to the speed of light, they are going to find that the period of oscillation of this pendulum is different. And we're going to figure out what that is. What do they measure that to be? Question mark. Okay, so our equation for time dilation is very simple. Delta t is equal to gamma times delta t naught. So here, this is the time for our moving observer. Okay, this is the time as measured by our moving observer. Okay, and this time, delta t0, that's the time measured by my person in the inertial frame. And so this is the person in the inertial frame who is moving with the experiment, okay? And our quantity gamma is 1 over the square root of 1 minus v squared over c squared, okay? And then we multiply that by delta t naught. This v is the speed at which my observer here is moving, all right? So now we can just plug in these quantities and figure out how long it takes from this observer's perspective here for that pendulum to complete one oscillation. And that's going to equal 1 over the square root of 1 minus the speed of our moving observer is 0.95 c, and I'm dividing that by c. Oh, maybe let's write it like this. So we're going to square this top number and c squared down here times the pendulum period in our inertial frame, that's delta t0, is 3 seconds. We're going to multiply that by 3 seconds. All right. So when we look at this problem here, okay, I've got 0.95 c squared all over c squared. So this c squared is going to cancel with this c squared. This becomes 1 over the square root of 1 minus 0.95 squared. Okay, this is the same thing as 1 times c squared. So if those c's cancel on top and bottom here, those c squareds, then I've got 0.95 squared by itself. Okay, and then we have to multiply this by 3 seconds. All right, and so then this is equal to, so 1 minus 0.95 squared, and when you take the square root of that, that is equal to 1 over 0.312. And then we have to multiply it by our original period of 3 seconds. And that gives us a time of 9.61 seconds. So my person who is moving at very close to the speed of light, who is watching this period oscillate, or this pendulum oscillate, is going to see that that period of oscillation takes almost 3 times longer, more than 3 times longer than the person in the inertial reference frame who is right there in the same room and not moving as that pendulum is swinging back and forth. So this is the idea of time dilation. And we also sometimes will say that moving clocks run slow. Moving clocks, oops, C-L-O-C-K-S, run slow. Okay, moving clocks run slow. So that means that whenever you're an observer moving very, very close to the speed of light, you are going to see something happen. And when you see that thing happen, it's going to take a lot longer time from your perspective for that event to take place. So weird things happen when you travel very close to the speed of light. The closer you travel to the speed of light, the bigger difference you're going to see between something happening in an inertial frame and something happening in your perspective as you're moving very close to the speed of light.
Let's recap length contraction. The length of an object measured in a reference frame that is moving with respect to the object is always less than the proper length. We defined the proper length, L sub naught, to be the length of the object as measured by an observer at rest relative to the object. And L is the length of the object measured in a reference frame that is moving with respect to the object. So L is going to equal the proper length divided by gamma. We're going to apply the idea of length contraction to a moving spaceship. An observer on Earth sees a spaceship at an altitude of 4,350 kilometers above the Earth's surface, and this spacecraft is moving downward toward the Earth with a speed of 0.97 times the speed of light. What is the distance from the spaceship to the Earth as measured by the spaceship's captain? And then for part B, after firing the engines, the captain inside the spaceship measures the ship's altitude as 267 kilometers, while the observer on Earth measures it to be 625 kilometers. What is the speed of the spaceship at this instant?
In this problem, we are going to apply the concept of length contraction. We have an observer here on the Earth, and they see a spaceship appear at an altitude of 4,350 kilometers. 4,350 kilometers. Moving downward toward Earth with a speed of 0.97 times the speed of light. So my spacecraft is moving with a speed of 0.97 c toward the Earth. What is the distance from the spaceship to the Earth as measured by the spaceship's captain? So we're going to be looking for this distance from the ship to the Earth as measured by the captain. I'll call that C captain equals question mark. Okay, so in order to solve this problem, we have to apply our equation for length contraction. So the equation for length contraction, L is equal to L naught over gamma. Gamma is 1 over the square root of 1 minus v squared over c squared. So down here we've got 1 over a square root. So dividing by a fraction is the same thing as multiplying by the reciprocal. So this will equal to L naught times the square root of 1 minus v squared over c squared. Okay, now we have to decipher which of these L's are which. Okay, which is the length in our inertial frame of reference, and which is the length from the moving observer's frame of reference in this equation here. So this L naught is what's measured in our inertial frame of reference. That's the frame of reference that is at rest. That's the frame of reference where the person doing the observing is not moving. So this L naught is what this person standing on the ground is seeing or is measuring. So this person on the ground measured the distance between the ground and the spacecraft to be 4,350 kilometers. So that's L naught here. Okay. Then L here is the distance measured by the spaceship's captain. The distance measured by the person who's moving at very close to the speed of light. So this is the distance that the captain is measuring. Okay? And so we have to find this distance. To do that, we're going to use this equation right here. So that equals the length as measured in the inertial frame of reference. That's the one that isn't moving with respect to our spaceship. And that length was 4,350 kilometers. And we're going to multiply it by the square root of 1 minus our velocity of the spaceship, 0.97 c. We square that all over c squared. Okay, so this c squared is going to cancel with this c, which will be squared. So this is equal to 4,350 kilometers times the square root of 1 minus 0.97 squared. Okay, and then this is equal to 4,350 kilometers times 1 minus 0.97 squared. We've got the square root of that, and that stuff underneath the square root sign is 0.591. There's no units on this number in here because our units that came along with c, our speed of light, cancel on the top and bottom. So we take 4,350 kilometers times the square root of 0.591, and we find that the distance to the ground as measured by our spaceship's captain is 1,058 kilometers. So this is length contraction. The person who is traveling at very close to the speed of light is going to observe distances to be much shorter than they actually are. For part B, after firing the engines, the captain measures the ship's altitude to be altitude is its distance above the ground, to be 267 kilometers, while the observer on Earth measures that distance to be 625 kilometers. What is the speed of the spaceship at this instant? So what we know is the distance to the ground as measured by the person who's traveling very close to the speed of light, and the distance that that spaceship is above the ground as measured by the person standing on the ground who is in the inertial frame. That person standing on the ground is not moving. The spaceship is moving with respect to this person. So this person is in the inertial frame, okay? And they're measuring that. So that's this measurement right here, L naught. They're measuring the distance that that spacecraft is above the ground to be 625 kilometers. But the spaceship's captain, because of length contraction, traveling very close to the speed of light, thinks that this distance is only 267 kilometers. How fast must they be moving? So we use our same equation that we had earlier for length contraction. L is equal to L naught times the square root of 1 minus v squared over c squared. And we're trying to solve this equation for v. All right, so we've got to do some algebra steps here in order to solve this equation for v. So we have to divide both sides by L naught. We've got to get this term by itself. So we've got to move everything over to the other side however we can. So we're going to divide both sides by L naught here. So L over L naught is equal to the square root of 1 minus v squared over c squared. Okay, and my marker's running out of juice here. Square root of, okay. Now we got to get rid of the square root sign. So we have to square both sides. We'll square both sides. That's the same thing as taking the top and the bottom here, squaring them. So the squaring the square root, that gets rid of the square root sign. So this is equal to 1 minus v squared over c squared. Okay. I've got to take this term right here and isolate it. This term has the v that I'm trying to get by itself. So what I'm going to do in this step is I'm going to take this term and move it to the other side. And then I'm going to subtract this term here and move it to the other side. Okay, so I'm going to add v squared over c squared. That's going to cancel it over here. I'm going to put it on this side. And then I'm going to subtract this term and move it to the other side. Well, maybe we'll just write it like this. L squared over L naught squared plus v squared over c squared equals 1. Okay, now I still have to get v squared over c squared by itself. So I'm going to subtract, here, I'll do this. Subtract L squared over L naught squared to the other side minus L squared over L naught squared. So now I'm going to bring us over here, over here, over here. I have v squared over c squared equals 1 minus L squared over L naught squared. Okay, almost done. I have to multiply both sides now by c squared. So I'm going to multiply this side by c squared, multiply this whole thing by c squared. It cancels this here and here. So now v squared is equal to c squared times 1 minus L squared over L naught squared. So then we have to take the square root of both sides to get rid of this v squared. Square root of both sides. So now this is v is equal to, whenever you have the square root of these things being multiplied by each other, we have c squared being multiplied by this thing squared, that's the same thing as c squared times c squared, the square root of that, times the square root of 1 minus L squared over L naught squared. Those are the same thing. Now, the square root of c squared is just c. So v here is equal to c times the square root of 1 minus L squared over L naught squared. Okay, woo! We did all of that algebra work, and now we are ready to plug in other quantities. So actually, what I'm going to do is I'm going to leave c as it is. I'm not going to put in the number 3 times 10 to the 8 meters per second. I'm going to leave it as c. So this is equal to c times the square root of 1 minus the length between the Earth and the ground from the perspective of the spaceship is, an observer in the spaceship, is 267 kilometers. And then I'm going to divide that by the length between the ground and the spaceship as determined by a stationary observer in the inertial frame. That was 625 kilometers. And then I have to square that whole term. We squared each of those individually. It's the same thing as putting the brackets around them and squaring that fraction. So our units of kilometers cancel on top and bottom here. So this is c times the square root of 1 minus 267 over 625 squared. And that is going to equal 1 minus the square root of 1 minus 0.182. Okay? And the square root of 1 minus 0.182 gives me c, let's write it like this, gives me a speed of 0.905 times c. So based on these quantities of what was the length between the ground and the spaceship in the inertial frame, and what was the length between the ground and the spaceship from the spaceship's frame, from an observer inside the spaceship, we were able to determine how close to the speed of light that spaceship is moving. And this spaceship is moving at almost 90% the speed of light.